Continuing with Unit 3, we're looking at Topic 8, representations of solutions. So we will be able to represent interactions between solutes and solvents, as well as the concentration of solutions using drawings. Using particulate models for mixtures. So particulate models can be used for, first, representing interactions between components of a mixture. So we want to show things like our proper size of our ions. Keep that in mind. We can show orientation of solute ions and solvent particles. So how are they oriented to represent their intermolecular forces, those interactions, and represent the concentration of the component. So we can also use diagrams to show molarity. Interactions between solute and solvent. So we've practiced this a little bit already in class with our table activity and some of our practice in intermolecular forces, drawing the attractions between different molecules in a mixture. So when drawing mixtures, another attraction is going to be added to our list. So far we've looked at London dispersion forces. We can see that example down at the bottom. We've got heptane and pentane, both hydrocarbon compounds with varying amounts of carbon and hydrogen. So those would have London dispersion forces and attract to each other in no particular spot. We've looked at dipole-dipole forces, which are in the middle there, the acetone and chloroform. So acetone has that red oxygen on it, making the dipole towards the right, and chloroform CHCl3 has the chlorines on one side and then that white hydrogen atom on the left side. So its dipole goes to the right towards the chlorines. So we have those dipoles lining up between our two molecules, making a dipole-dipole force. And last, we have hydrogen bonding. We can see the ethanol, so ethyl alcohol with that OH part at the end, the red and white, attracting to our water. So we've got the hydrogen from the ethanol, the white atom, which is sandwiched between oxygen atoms, one that it's bonded to in ethanol and one that it's attracting to in water, creating the hydrogen bond. So these all occur between covalent molecules, which is why they are called intermolecular forces, because they are between molecules. All right, sorry about that bell. Let's take a look at a sample free response question that's a little different than just explaining an intermolecular force. So it says urea has a high solubility in water due in part to its ability to form hydrogen bonds. A urea molecule and 4 water molecules are represented in the box below or the one on the right. As I moved it, draw one dashed line to indicate a possible location of a hydrogen bond between a water molecule and the urea molecule. So we've got the urea in the middle. We do have a key to let us know what element is what, and then we got our 4 water molecules. Now we want to be really careful here and pay attention to our directions. We want to draw one dashed line, and they show us what that should look like. We don't want to draw something different than what they're telling us to do. Okay, so we need to locate a place where we can have some hydrogen bonding. So we've got water molecules. We know they can all hydrogen bond. In our urea molecule, we've got an oxygen up here, but it's not attached to a hydrogen. We've got a carbon. We've got 2 nitrogens, each with hydrogens attached. So those could hydrogen bond. So we could hydrogen bond from our urea to water, or from water to the urea, to the nitrogen. It'd be a little harder with the nitrogen. So I think the easiest one is probably this one over here, hydrogen sandwiched between nitrogen and oxygen, showing that one dashed line. Other acceptable ones would be drawing a dashed line here. You could draw a dashed line from this oxygen to this nitrogen, or this hydrogen to this oxygen. So you've got a couple of options, but we only want to draw one of them, okay? And it's always most logical to draw ones that are nearest to each other. So I wouldn't probably want to try and draw one, I'll do this one in green, like from this oxygen to the hydrogen. It's a little further distance, go to the one that's closer. It's more likely to attract, but if it's the right combination of elements, they're going to count it on the AP exam. Now, as mentioned prior, we still have one more type of force that can occur. So the last force we can look at comes from the mixture of ionic compounds with polar solvents to create a solution. So this is called an ion dipole force. We've heard of dipole forces, so that's two polar molecules attracting. So that tells us in the name exactly what it is. Here, it's just as similar. We need an ion from one chemical and a dipole from another chemical to form ion dipole forces. So the reason I haven't introduced these previously is because this is in a mixture of chemicals, all right? You can't have ion dipole forces with just one chemical because you need something ionic to produce the ions, and you need something covalent that is polar to create the dipole. So it has to be a mixture, okay? So this is perfect when we talk about solutions. So ions from ionic compounds and dipoles from polar molecules can attract each other. The ions have a full positive or negative charge, which can attract to the partial positive or partial negative created by the dipoles. So here we can see our sodium chloride ions breaking apart and being surrounded by water molecules. So our negative chlorine here attracts to the positive side of the water molecules, the positive dipole on those water molecules. We got that dipole going, oops, drew it backwards. Dipole goes towards our oxygen, so the positive part of it attracts to the negative chlorine. And then our negative part of our dipole over here points towards our sodium, so the oxygen side attracts to the sodium. Oops. So that is a very key situation here, is the arrangement of the atoms. So it says, notice the directions the water is turned. This is a type of question that I've seen on the AP test, is drawing in your water molecules or labeling the ions and making sure that you're paying attention to charges. A big thing here too is when we're showing these ions, we need to show their charges. So if I write chlorine, I can't just write Cl. I have to write Cl minus. I have to write Na plus to show that they have charges, right? All right, we're going to take a look at drawing a representation of a mixture of magnesium chloride dissolved in water. So this is a practice question similar to things we've seen on the AP exam in the past. So let's just first look at how magnesium chloride breaks down. So we separate our ions, magnesium and chlorine. Our subscript comes to the front, and then we can check our charges. So chlorine's always negative, magnesium's a 2+ based on their columns on the periodic table. So this is how it breaks down. We've separated our ionic compounds in chemical bonding in that unit. So this is the same idea here. So when we dissolve magnesium chloride from a solid form, it becomes aqueous ions. So that's actually a chemical, kind of how we can write a chemical reaction for something dissolving. But if we want to show the picture part, I'm just going to draw it down here. We want to draw each of our ions. So we've got magnesium 2+. You could even just do a circle with a 2+ charge would be a nice representation. And then our chlorines. Now a big thing that I see a lot of students do is trying to attach the chlorines to each other, or attach the magnesiums and chlorines to each other, or writing just Cl2 like it's diatomic, but we want to separate each of the ions. So we should end up with 3 ions here. And then we want to show it dissolved in water. So I'm going to change up my color here to show our water. Magnesium is positive, so it should attract to the negative side of water, which would be our more electronegative atom, which would be the oxygen. So we're going to draw a few waters around it with the oxygen towards magnesium. I know it's the oxygen because it's H2O. Oxygen has a bigger radius, and then the hydrogens are like little ears on Mickey Mouse. So we want to make sure we're interpreting that properly. An oxygen with 2 hydrogens, okay? Sometimes they'll even give you a picture of how to set that up. We could even shade in like our oxygen or our hydrogens to set them apart and show that they are different. But we want to make sure that negative oxygen side is towards magnesium. Then if we're going to do chlorine, we want that positive part of our molecule, the partial positive of the water, which would be our hydrogens, to be facing towards the chlorine, right? So these attractions represent ion dipole forces. We've got an ion, we've got a polar molecule with the water, which has a dipole. So we've got ion dipole forces. So if we showed an attraction between these, any of these, that would be an ion dipole force. Okay. If I just said magnesium chloride, MgCl2, I cannot have ion dipole forces. If it was just water, I cannot have ion dipole forces because one is an ionic compound and one is a polar molecule. You can't have two types of things happening with that same, with just one chemical. All right, let's take a look at some more examples. So which of the following diagrams best represents the silver nitrate solution? Note, water molecules are represented by this symbol. So we can see that Mickey Mouse molecule, as I like to call it. So again, that's H2O. So we've got hydrogens, two hydrogens and an oxygen, H2O. So silver nitrate, if we broke that down into its ions, we would get silver, right? We break off our metal. And then nitrate, our polyatomic ion. Nitrate we know is negative, so silver must be positive. So in each of these, we can see that this in A, B, and C, the silver and nitrate are separated. D, they are together. That is incorrect. So I'm going to go ahead and eliminate that answer. Then we want to look at our water molecules. I can see in my first one, the waters are oppositely turned. In my second one, they are turned the same way. Or no, some of them are opposite. But we can see around the silver, they aren't all turned the same way. So that's a little odd, right? This one's not turned and directed the same way as that one. That can't happen. So I'm going to eliminate B. That's happening here as well. They need to be turned the same way all the way around the molecules, or the ions. Let's check letter C. We've got the oxygen turned towards silver and towards nitrate. So that can't be the answer either because they can't both be turned the same way. So A must be our answer. Let's check it. So we've got our oxygen part of our water here. That's the negative part attracting to the positive silver. So that's good. Check. We've got our positive part of our hydrogen attracting to the negative nitrate ion. So that's correct. So there's our ion dipole force. That's a correct representation of the silver nitrate solution. All right. Let's take a look further at silver nitrate. So it says, or excuse me, at silver chloride. So it says student mixes dilute silver nitrate, so what we saw in the last slide, with excess silver or sodium chloride to form silver chloride solid, as represented by the net ionic equation above. Now we haven't looked at net ionic equations above, but we can see that the silver from the silver nitrate and the chlorine from the sodium chloride are coming together to form a solid. So that means that part's insoluble. And we can see in all the pictures that that solid is chunky at the bottom. Okay. So we want to know which diagram below represents the ions that are present in significant concentrations in the solution. Okay, so when it says we have an excess of sodium chloride, they have extra of those to make sure all of the other chemicals, all of the silver or the nitrate reacts. So we're making sure we've used up all that silver. So we should see no silver ions in our beaker. So A is a good contender, but B has a whole bunch of silver in there. I'm going to cancel that out. C is a good contestant, and D has some silver in there, so let's eliminate D. So now we're between A and C. So we want to see what makes sense here. So we've got excess of this, so we should have some sodium ions in there. So A has a bunch of sodiums, I'm good with that, and B has some, C has some sodiums, we're good with that. They have nitrate ions in both, so we're not using up the nitrates, so we should still have some nitrates there. And then since we have excess sodium chloride, we should probably have some extra chlorines. They probably didn't all react. So C would be our better option because we're going to have all the silver reacted and then some extra chlorines that didn't. Okay, so we've got those extra chlorines here and here. So that would be our answer for this one. All right, here's another good example of drawing a representation. So the structure of water molecule and crystal of lithium chloride are represented below. Show the interactions of components of lithium chloride aqueous by making a drawing that represents the different particles present in the solution. Base the particles on your drawing, on the particles shown in the representations below, include only one formula unit of lithium chloride. So we want one lithium and one chlorine. So we got to keep that in mind. So we want one set, lithium and chlorine, and no more than 10 water molecules. Okay, no more than 10. So we can have a few less, but no more. Okay, so we've got lithium and chlorine. First, we want to decide which picture represents lithium and which one will be chlorine. Lithium, when it's Li plus, loses its energy level, so it only has one energy level. Chlorine, when it's negative, has filled in its third energy level, so it's 3. So that's much bigger. So chlorine's going to be our larger atom, and then lithium's going to be the smaller ion. So I'm going to do my small lithium and my larger chlorine that's shaded in, so I know who's who. And I want to know which one's which, so I know which way to turn my water molecules. So if lithium is positive on the left, I want my water to have the negative side towards it. So I'm going to do this and put a few water molecules around it. And my chlorine is negative, so I want the positive part, the hydrogen part of my water, to be towards my chlorine. So that would be a correct representation of our solution. All right, so now we can represent concentration as well. We've looked at how we can represent the different interactions between particles, but now we want to look at concentration. So if a question discusses concentration, so molarity essentially, then we need to be aware of the molarity of the chemicals given. We need to make sure we check out the chemical formula and think about the number of ions shown in our pictures as we draw them. So we want to keep those things in mind. So if you're looking at the molarity, we want to remember that diluting does not change your number of ions. So if we're looking at a picture that dilutes something, our number of ions won't change, but the volume and concentration will. When we're thinking about the chemical formula, it will help us determine the number of ions and what the ratio is to each other. So just like we've been looking at, we want to separate the chemicals into their ions, just like we practiced in chemical bonding, and determine the number of positive and negative ions so we know their ratio. And be sure to count your number of particles in your picture so that we know we have the correct amount. So what does this look like? Equal volumes of solutions in two different vessels are represented below. So this is an example problem. We've got 2 containers with our chemicals represented. If the solution represented in vessel 1 is KCl, so let's label that. Then the solution represented in vessel 2 could be an aqueous solution of, and our 2 options are KCl and CaCl2. So let's just look at these 2 chemicals. If this breaks down, we're going to get potassium ion and chlorine ion, one of each. If calcium chloride breaks down, we still get that Cl minus, but we have 2 of them. And then we've got that calcium ion, and it's a group 2 metal, so it's a 2+ charge. So we have a 1-to-1 ratio and a 2-to-1 ratio. So we want to look at what our ratio of chemicals are in these. So we know our first chemical is KCl, and we can see we have 4 of our positive ions, so the black ones are any positive ion, and we have 4 of our negative ions. So we have 4 to 4 in terms of our ions. So that's keeping the same ratio. 1-to-1 is the same as 4 to 4. And then let's look at our comparing our amount of positives and negatives in the second vessel. So our positives, the black ones, we've got 1, 2, 3, 4, 5, 6, 7, 8 positives and negatives. We got to count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, 8 to 16. So in this one, positive to negative, we have a 2-to-1, or excuse me, I wrote that backwards. My bad. And I wrote it backwards down here too. It's a 1-to-2 ratio with twice as many chlorines, and it's the same up here. It's a 1-to-2 ratio with twice as many of our negative ions. So our second vessel is going to have something with a 1-to-2 ratio. So it can't be KCl. It has to be the calcium chloride. So we've at least eliminated 2 of our answers. That's half the battle, right? Now we want to look at our concentration. So it says calcium chloride with the same molarity as a solution in vessel 1, or with twice the molarity. Well, to determine how the molarities compare, we can just pick one of our ions. And I'm going to pick my positive ion because if I look at my ratio, it's 1 to 1 here and 1 to 2 here. So I should have equal amounts of my positive ion if they're the same molarity. But I don't have equal amounts. I have a 4 in my KCl and 8 in my calcium chloride. So that means that the molarity must be twice as much because I have twice as many positive ions. And we can also see we have 4 times as many negative ions. So that's a much greater concentration. So we have letter D, calcium chloride, because of the number of particles, the ratio of particles, 1 to 2, and it's twice the molarity because we have twice as many of each ion compared to our first container. All right, and let's look at one last example on the next slide. Actually, not an example, sorry, just our conclusion. So particle or particulate representations of solutions communicate the structure and properties of solution by illustration of the relative concentrations of components in the solution and drawings that show interactions among those components. So these drawings, we really don't want to just look at them and say, oh, it's a picture of a solution. We want to say, look at things like how many ions are there? What directions are water molecules or ions turned? How are things interacting? What's the ratio of ions or elements? And all of those are going to help us answer questions about those pictures or help us draw those pictures. I hope that helps. Let me know what questions you have. Thanks, guys.